Okay, hello. Today we're going to be talking about indices and surds. This is week 2 of our math course. So in our last lesson, we were looking at algebraic expressions and we were focusing on expanding brackets and also factorizing, particularly factorizing quadratics. We looked at both monic quadratics and non-monic quadratics. So hopefully you had a chance to go through the practice exercises, treat it like a test, and check your answer. Today, we're looking at indices and surds. So I want to start with a few warm-up questions just to get the juices flowing. Please take a moment, pause the video, and decide your answers to these questions. 2 cubed is 8, the square root of 49 is 7, 3 squared is 9, the square root of 25 is 5, and 4 to the power of 1/2 is 2. If you don't know what's going on here, you're going to find out today. I want to point out one thing here. If we have an equation that says x squared is 49, then we know that x must be plus or minus the square root of 49. So it could be the positive square root or the negative square root. I just want to point that out because over here where we say the square root of 49, there's no plus or minus in front of it. That tells us we're taking the positive value. So if you put plus or minus 7 or plus or minus 5, this is not correct. We are only taking the positive value. If we said negative square root 49, we would say negative 7. Okay, this is something you could argue about, you could have a different opinion, and that's actually okay, but this is the way we do it. This is the convention that we follow in mathematics. So if you're asked for the square root of 25, you don't need to say whether it's plus or minus. You can just say 5. However, if you're told that something squared equals 49 and you're asked what that thing is, it can be plus or minus, and you do have to include it. To start with, I'm going to introduce the index laws. There are 6 that we're going to look at. These terms here, index, power, exponent, and order, all refer to the same thing. You're probably used to, from earlier years, talking about x to the power of 3, right? Now, 3 is the index. If we have more than one index, they're called indices. Exponent, you'll probably recognize from the word exponential, and that also has to do with the power. And finally, order, we discussed last week, we were looking at different polynomials and talking about the order of the polynomial, and that referred to the highest power of x within the polynomial expression. So we have all of these terms, all of these different ways of saying power, but what does it mean? What is a power? Well, a power is the number of factors of a value that we're multiplying by. Okay, so that means if we have x to the power of 3, we're multiplying 3x's. Okay, so this makes the first index law really easy to understand. We call it the product law. So if we have a to some power times a to another power, now it's really important you pay attention. The a's have to match. If the base number is not the same, this law does not apply. So if we have a to the power of m times a to the power of n, we just add those powers together. So let's look at some examples to explain that. Firstly, if we have 3 to the power of 4 times 3 to the power of 2, the 3 to the power of 4 means we have 4 3's multiplied together, and then we're doing times 3 to the power of 2. Now we don't need these brackets, and if we get rid of them, what we realize is that we have 6 3's multiplied together. So we took the first 4 3's, and the second 2 3's, we added how many 3's we're multiplying. We can do it without a 3. We could have x to the 5 times x to the 3. So 5x's, 3x's, that means we have 8x's in total. So we're adding the power. Finally, we can have more than 2 altogether, right? So 2 to the power of 3 times 2 to the power of 2 times 2. So that's 3 2's and 2 2's and 1 2. Here where we don't put the power, that means there's a 1. There's a sneaky 1 up the top there. So we're adding 3 plus 2 plus 1, which is 6. That's 2 to the power of 6. Okay, we're going to move on to this question in a second, but first I want to give one more example. Because the base number is not the same, we cannot apply the product index law straight away. We can't just say it's 2 to the power 5 or 6 to the power 5. Neither of those is correct. But we can do something, and that is because 6 is 2 times 3. So this is 2 to the power of 3 times 2 times 3 to the power of 2. Now, this is foreshadowing something that's coming. I'm actually going to explain how we deal with these brackets later, but right now, just assume you understand. So we have 2 to the power of 3 times 2 to the power of 2 times 3 to the power of 2. That power of 2 outside got applied to both of these things inside. And so we can now apply the index law for the first two terms because they both have a 2. So that's 2 to the power of 5 times 3 squared. And applying our index laws, this is the best answer we can get for this question. Okay, now let's think about what it means if the power is 0. Consider, if we have 2 times 3 squared, we're taking 2 and we're multiplying it by 3 twice, which gives us 18, right? 2 times 3 is 6, 6 times 3 is 18. In the second case, if we have 2 times 3 to the power of 0, that means we're taking 2 and we're multiplying it by 3 0 times. In other words, we still have 2. This tells us that when we multiplied by 3 to the power of 0, we were doing the same thing as if we multiplied by 1. And so this gets us into the second rule that I want to talk about today, which is that anything to the power of 0 is equal to 1. I like to imagine that the 0 is a little balloon, and in every question, someone is holding the balloon. So up there, a to the power of 0, a is holding the balloon. Here, 7 is holding the balloon. Here, x is holding the balloon. Now, here's where it gets different. In this question, x is holding the balloon, and 3 is not. So the x is the thing to the power of 0. So we have 3 times x to the power of 0, which is the same as 3 times 1, and we just get 3. But have a look at this final example. Because of the brackets in this example, the 3x, they're holding the balloon together. So together, they are equal to 1. This is something that can trip you up. Even though this is a very simple and easy to understand rule, anything to the power of 0 equals 1, you can get tripped up very easily if you're not paying attention to who is holding the balloon. We can have positive powers and we can have powers of 0. What if we have a power less than 0? So here's the spoiler. A to the power of a negative number is equal to 1 over a to that number. This means it's like we're dividing by a m times. Okay, so if we have a to the m, we're multiplying by a m times. If we have a to the negative m, we're dividing by a m times. And typically all we're going to be asked to do is to rewrite with a positive index, which means if you have x to the power of negative 5, we just say it's 1 over x to the power of 5. If you have 2 to the power of negative 3, that's 1 over 2 to the power of 3, and we can evaluate that. That's 1 over 8. 2 to the power of 3 is 8. Okay, now in example 3 here, I've included many steps, but really I just want you to focus on the last one. All of these steps are there in case you don't believe the last one. You can pause the video and go through step by step. This explains how we get here. But the key thing is, right, let me write this in a different way. A could be a on 1. And then this is equal to 1 on a to the m, or in other words, 1 on a to the m. Okay, so when we have a negative power outside a fraction, we just take the reciprocal of the fraction. We flip it upside down. So 3 over 4 to the negative 2 is 4 over 3 to the power of 2. Or we could write it as 16 over 9. We can prove this index law using some algebra. So for example, if we know that x to the power of m times x to the power of n is equal to 1, right? We're just assuming this. This is the first step of this proof. That means using our product rule, our product law, we can say that x to the power of m plus n is going to be equal to x to the power of 0, right? Because x to the power of 0 is 1. So now we can say both sides of the equation are x to some power, and they're equal, which means that the powers have to be equal. So m plus n must equal 0, and therefore we can say n is equal to negative m, okay? This actually segues into our next index law, which we call the quotient law. If we have x to the m times x to the n equals 1, right? Familiar, we've got it just up there. But we use our conclusion. We know for this to be true, n must be negative m. That means x to the m times x to the negative m is equal to 1. And so now we can get this conclusion here. The quotient law should say, if you have x to the m over x to the n, which is the same as x to the m divided by x to the n, this will be equal to x to the m minus n. How do we know this? So let me add this extra little explanation up here. That's like x to the m times 1 over x to the n, okay? And if we follow through with what we know, that's x to the m times x to the negative n. And now using our product rule, we add m and negative n. So we have x to the power of m plus negative n. And so again, this is another derivation of the same thing. This is our quotient law. Now we have the power of a power rule. So a to the power of m all to the power of n is a to the power of m times n. Let's look at some examples. If we have 2 to the power of 3 all to the power of 4, here we have in brackets our 2 to the power of 3, and then we're going to have it 1, 2, 3, 4 times, right? That means that we have 3 times 4 factors of 2. In other words, we have 2 to the power of 3 times 4. In our next example, we have x to the 5 all cubed. So here we have 5 x's multiplied together, and we do that 3 times, which leaves us with 15 x's. Now we can even go a little bit further. I'm going to zoom out a little bit for this one because there's a lot going on. If we have a squared cubed to the power of 4, well, here we have a squared cubed, and then we do that to the power of 4. So each of these brackets has 6 a's in it because that's what a squared cubed gives us. There are 6 a's in there. And so then we have that 4 times. So in total, we have 2 times 3, which is 6 a's, times 4, we have 24 a's. All right, so we've seen how we can have powers that are added. We can have powers that are subtracted. We can even have powers that are multiplied. Can we divide them? Of course we can. We can have fractional indices. And here's the rule right here that governs it. If you have a fractional index, the numerator in the fraction is the power we are raising to, and the denominator represents a root. So let's look at an example real quick. If we have 9 to the power of 1 over 2, that's the square root of 9 to the power of 1. Now, 9 to the power of 1 is just 9. So the square root of 9 is 3. 9 to the power of a half is 3. If we have 16 to the power of 3 over 4, well, that is the fourth root of 16 cubed. Now, notice that this squaring, or this raising to the power of 3 and taking the fourth root, these are commutative operations, and that is a fancy mathematical term that means we can do them in different orders. So we could do 16 cubed and take the fourth root, but it's actually easier to take the fourth root of 16 and then cube the answer. So the fourth root of 16 is 2. We cube it. We find that 16 to the power of 3 over 4 is 8. 27 to the power of 2 over 3. We start by taking the cube root of 27, which is 3, and then we square it, which gives us 9. All right, so we need to have all of these 6 rules written down. I'm going to pull them up here so that you can see them all at once, and I want you to have them all written down in front of you. You need these rules to be as easy for you to understand as the recipe for preparing a glass of water. These might seem a little confusing and overwhelming right now, but these are all really important and you need to know them well. So let's just quickly recap. Anything to the power of 0 is equal to 1. If you multiply something to 1 power times the same thing to a different power, you can simplify that by saying it's that number to the sum of the powers. We have a negative index law, which says that a to negative m is the reciprocal of a to the m. We have the quotient law that says if we have am over an, or am divided by an, that is equal to a to the power of m minus n. I don't think of this as its own rule. It is taught that way in schools, but this is really just a combination of these two things here. It's the product law using a negative power. Then we have the power of a power rule. So something to 1 power all raised to another power is that thing to the product of those two powers. And finally, the fractional index law. So if we have a to the power of m over n, that is the nth root of a to the m, or that is the same as the nth root of a raised to the power of m. These are equivalent. So I want you to make sure you've got everything from the index law section here written down. Surds. The term surd comes from the word absurd. This is because these numbers were once thought to be impossible. In other words, it was believed that every number that isn't a whole number can be written as a fraction. Surds proved that belief wrong. Now, a number that can be written as a fraction is called a rational number. It can be written as a ratio. And a number which cannot be written as a fraction is an irrational number. It cannot be written as a ratio. The first known proof of an irrational number is attributed to a man called Hippasus. He was an ancient Greek and he was a member of the cult of Pythagoras. He probably never met Pythagoras. Pythagoras died when Hippasus was like 5 years old. but he was into maths and he was into Pythagoras' cult. Now, the Pythagoreans believed all numbers must be rational. Hippasus proved that the square root of 2 is irrational, and the Pythagoreans were like, okay, you're wrong, so don't publish this. But he published it anyway, and they were so angry that he published a proof contradicting their beliefs that they took him out to sea in the Mediterranean and tossed him overboard. So, the stakes are high. Let's not make a mistake. Let's make sure that we know what's going on, because some people really care about this. Now, Hippasus' proof is quite elegant. It's a nice one. I'm not going to cover it today because it's not relevant to what we're studying right now. But right now, take my word, surds are irrational. And that's why we write them as surds instead of simplifying them to something else. So every surd is a square root of an integer which does not have an integer square root. Okay, so you'll notice that in this list, I haven't got the square root of 4. It's not a surd because it has an integer square root. The square root of 4 is 2. Same thing for 9. The square root of 9 is 3. But all of these others, they do not have integer square roots. However, some of them can be simplified. Because the square root of 8, for example, has a square factor, which is 4. So the square root of 8 is the square root of 4 times 2, which is the same as the square root of 4 times the square root of 2. And the square root of 4 we know is 2. So the square root of 8 is equivalent to 2 root 2. Cool. Let's look at a few more examples. So the square root of 50 is the square root of 25 times the square root of 2, or in other words, it's 5 root 2. So what we're looking for when we're trying to simplify is there a square number that is a factor, right? So 72 has a factor of 36. So it simplifies to 6 root 2. Or 48 has a factor of 16, so it simplifies to 4 root 3. Now, just like we add and subtract like terms, we can do the same thing with like surds. So 3 amounts of root 5 plus 2 amounts of root 5 give us 5 amounts of root 5. Or 4 amounts of root 7 minus 1 amount of root 7 leaves us with 3 amounts of root 7. We can also multiply surds. So the square root of 3 times the square root of 12 is the square root of 3 times 12, which is the square root of 36, and that is no longer a surd. It is now 6. Or we can be expanding brackets. So following FOIL, we have our firsts here, our outsides, our insides, and our last. Now this is the difference of two squares. You should recognize that from last week. And that means that these two terms disappear, they cancel out, and so we get a nice answer in the end. Okay, now we've used the difference of two squares for a reason, and that's because we're about to learn to do something called rationalizing a denominator. We can't always get rid of surds, but we can get them out of our denominators, and as a convention, this is something that we like to do. It makes things easier if we're trying to do operations with lots of fractions that have surds for us to make the denominators rational numbers. Okay, so how do we do that? In example 1 here, we have the surd 1 over the square root of 3, and we have a surd in the denominator. So what we do is we do something very sneaky. We multiply it by 1, but we write 1 in a very specific way. Okay? Anything divided by itself is equal to 1. So the square root of 3 over the square root of 3 is 1. But by choosing to write it this way, it means that our denominator is now root 3 squared, right? Square root of 3 times square root of 3, so it becomes 3. So 1 over root 3 is equivalent to root 3 over 3, and we tend to favor writing it this way because this means we have a rational denominator. Okay, next example, 5 over root 2. So we're going to multiply by root 2 over root 2, and that's going to give us 5 root 2 over 2. And again, we favor this way of writing it because it has a rational denominator. Now, the difference of two squares is about to come back, and it's going to come in really handy. If we have an expression like this one, 2 over 3 plus root 5, we're going to use the difference of two squares in our denominator or in our fraction to make our denominator rational. If we were to expand out 3 plus the square root of 5 multiplied by itself, we wouldn't get rid of the surds because we would have two amounts of 3 times the square root of 5 left over. But when we do it with 3 minus the square root of 5, right, when we flip the plus to a minus, now we're using the equation or the formula for the difference of two squares. And so that denominator is going to give us 9. Instead of 9 plus 6 root 5 plus 5, we have 9 minus 5. Okay, so notice we have to deal with the multiplication in the numerator, right? This becomes 6 minus 2 root 5. And then our denominator simplifies to 4. And then now we can simplify this fraction by dividing the top by 2 and dividing the bottom by 2. And this is where we finish. Here is a really important note. When you answer a question and find that your answer is a surd, you have a choice to make. Do you give your answer as a surd, or do you use your calculator and round your answer to a decimal? If the question says to give your answer as an exact value, then you must leave it as a surd. If you take a decimal, even if you write all the digits your calculator shows you, even your calculator is rounding it, because a surd, it has a decimal expansion that never ends and never repeats. So there's no way you can write it perfectly. The only way you can write the exact value is if you leave your answer as a surd. If you've been asked for an exact value and you do not give your answer as a surd, you will not get full marks. Those concepts are fairly straightforward. Now, I'm going to do a heap of examples because I want you to see many ways of how these problems can be asked and how we can approach them. I would recommend that you take a moment just to attempt these examples here. And then once we've had a go at each of these, we'll move on to the worded problems below. So pause the video now, and I'm going to answer them myself. So for question A, we are going to expand these brackets. And that basically means that this power of 2 gets multiplied by all of the powers that are in here. So that becomes an 8. This is a negative 6. Now this 2 has a sneaky power of 1, which is now a 2. I don't really need to write it as 2 to the power of 2. I can simplify that as a 4. Now the one thing that I'm also going to do is I'm going to put this in the denominator. It is generally considered good practice to rearrange things so that you don't have negative powers. You want to rewrite with positive indices. All right, so now we have B. Here we have these two factors of x on the bottom. I'm going to move them to the top, make them a positive power. I'm going to take these three factors of y, put them on the bottom, make them a positive power. That means that this is now going to be y to the power of 4, and then on top, we're going to have x to the power of 7. Cool. All right, next one. 81 to the power of 1/4. So that's, what is the fourth root of 81? I happen to know the answer to that. It is 3. 27 to the power of 1/3. What is the third root of 27? I happen to know the answer to that. It is 3. 3 times 3 is 9. What we're doing here, we can't add or subtract these surds because they're not like surds, but we can simplify them. In this case, 27, that's 9 times 3. 12 is 4 times 3. And 75 is 25 times 3. Okay, so pulling out our square factors, that 9, when we square root it, becomes a 3. When we pull this 4 out of the square root, it becomes a 2. And when we pull this 25 out of the square root, it becomes a 5. Now note that now we have like surds. We have 3 amounts of root 3. We add 2 amounts of root 3, which means we have 5 in total. And then we subtract 5 amounts of root 3, which means the answer is 0. Okay, now, next one. We're going to need to add these. When we add fractions, we need the denominators to be equal. When we add fractions, we need the denominators to be equal. And so what we're going to do is we're going to multiply the denominators together. Now that is actually really nice in this question because it means that we're rationalizing the denominator at the same time because we're doing this approach, which is using the difference of two squares formula. Now, whatever we multiply on the bottom, we have to multiply on the top as well. So let me just do that. Okay, so we're going to have 5 minus 4 as our denominator for both. This is going to be 6 root 5 plus 12, and this is going to be 2 root 5 minus 4. Now that 5 root minus 4, that's 1, okay? And because we have 1 on the denominator, we don't even need to write them as fractions. Now we can deal with our like terms. So 6 root 5 plus 2 root 5 gives us 8 root 5. And then we have 12 minus 4, which gives us 8. And so this is our answer. And if we want to be smarty pants, we could say that this is 8 times root 5 plus 1. But why bother? It's fine, just like this. We do not need to factorize it. Okay, so 64 to the power of 2 over 3. That means we're doing 64, we're taking the cube root, and then we're squaring it. The cube root of 64 is 4. Let me write my working out like this. We have the cube root of 64 squared, which is 4 squared, which is 16. So in this one, because we had the negative power, the first thing I'm going to do is make it positive by taking the reciprocal of the expression. And now we're going to take the square root of 9, which is 3, and we're going to cube it. And so our final answer will be 1 over 27. Now to rationalize this denominator, all we have to do is we have to multiply by a fraction, that is equal to 1, that's going to get rid of that square root on the bottom. So this is going to give us 5 root 8 over 8, and that's it. We're done. In this next example, we're going to have to multiply by a fraction that combines with this denominator in the same way as the difference of two squares formula, which means that will be a negative and that will be a negative. So what that means is in our numerator over here, we're going to have to multiply by that, and in our denominator, we're going to multiply by that. Down here, we're going to end up with 9 minus 2, and in our numerator, we're going to have 12 minus 4 root 2. The denominator becomes 7, and there is nothing else we can do. We're done. Okay, so I hope that those all made sense for you. Now I want to go through these worded problems. Again, I would recommend that you pause the video between each one, attempt it yourself, and then compare what you did to what I do. So I'm going to start now with question 1 here. A radioactive substance has a mass of 200 grams and decays according to the equation where the mass is 200 times 0.5 to the power of t. So m is the remaining mass, t is the number of hours it's been. So firstly, find the mass remaining after 6 hours. Okay, so that means for A, the mass remaining will be 200 times a half, right? 0.5 to the power of 6. In other words, we're multiplying 200 by half 6 times. Okay, so let's see. If I halve 200 6 times, one time gives us 100, then 50, then 25, then 12.5, then 6.25, then 3.125. So that means that the mass will be 3.125 grams. Next, how many hours will it take for the mass to fall below 3 grams? Well, if I halve this one more time, just one more time, it's going to be less than 3 grams. This is after 6 hours, so just one more hour will be enough. So it will fall below 3 grams after 7 hours. Notice I'm including the units with my answer. If you did not include the units with your answer, that's a problem. Pay attention to it. And C, suppose a new substance follows this equation. So this equation is the same, except instead of the thing that we're raising to a power being a half, it's now a quarter. So how does this compare in terms of decay rate? Well, it means we're decaying much faster because instead of every hour having half of the substance left, every hour we have a quarter of the substance left. It is decaying much faster. That's enough. We can move on. All right, pause the video, have a go. A square has a side length of 2 root 3. There should be some units here. Let's call it meters. So here is my square, and the side length is 2 root 3 meters. Now the exact perimeter, so A, P for a square is 4 times the side length. In other words, 4 times 2 root 3. And so that's just going to be 8 root 3 meters. Find its exact area. Area is the side length squared. So that's 2 root 3 squared, which is going to be 4, that's the 2 squared, times 3, which is root 3 squared. In other words, 12 meters squared. If we draw a diagonal across here, that means we're going to have Pythagoras' theorem says that that diagonal is going to be equal to the square root of the square of the other two sides. And we know that the other sides, if they're squared, are 12 meters. So it's going to be 12 plus 12. In other words, we're looking at the square root of 24. We can pull out a square factor of 4, so that's 2 root 6 meters. Let's go on to the next one. Have a go. If you've had a go, let's look at it together. If 2 to the power of x is 128, we can approach this with trial and error, right? So if you try a few different powers of 2, you'll find that 2 to the power of 5 is 32. 2 to the power of 10 is 1024. So it's going to be between 2 to the power of 5 and 2 to the power of 10. I happen to know that 2 to the power of 7 is 128. Similarly, I've already given this answer to an earlier question. 3 to the power of 4 is 81. Okay, so for A, we can say x equals 7 and y equals 4. Now for B, 5 to the power of 2x equals 325. Let's think about the powers of 5 real quick. 5, and then square, we get 25, multiply that by 5, we get 125, multiply that by 5, we get 625, multiply that by 5, we get 3,125. Okay, looking good. So this is 5 to the power of 1, 2, 3, 4, 5. So this tells us that 5 to the 2x is the same as 5 to the 5, which means that 2x, the power on the left-hand side, must be equal to the power on the right-hand side, and so x is 5 on 2. Cool, okay. And finally, C, find the value of z if 4 to the power of z plus 1 equals 32. 4 to the power of z plus 1 equals 32. Well, 32 is 2 to the power of 5, and then this is 2 to the power of 2 to the power of z plus 1. In other words, 2 to the power of 5 is equal to 2 to the power of 2z plus 2, right? We're using the power of a power index law. Okay, now let me just continue this over here because I'm running out of space. If both sides are 2 to a power and they're equal, then the powers must be equal. So 2z plus 2 equals 5, which means 2z equals 3, which means z equals 3 over 2. Question 4. Pause it, have a go. A company's revenue follows an exponential growth pattern given by that there, where R is the revenue in dollars and TTT. Why I got so many T's here. T is the number of years. Find the revenue after 4 years. So A, I'm going to say revenue is 5,000 times 1.1 to the power of 4. I think we can just use a calculator for this. 5,000 times 1.1 to the power of 4 is going to give us 7,320, 7,320 and 50 cents. How long will it take for the revenue to exceed 15,000? The way I'm going to approach this is I'm going to type in 5,000 on my calculator. I'm going to press equals. Now I'm going to press answer times 1.1. Okay. So when I press equals, it will be like doing 5,000 times 1.1 to the power of 1. So that's after 1 year, we have 5,500 revenue. If I press equals again, it gives me after 2 years, we have 6,015 revenue. Press it again, 6,655. Press it again, we get 7,320.5. So we're up to 4. I'm going to count how many times I need to press it to get over 15,000. 5, 6, 7, 8, 9, 10, 11, 12. After 12 presses, we have now exceeded 15,000, which means that it will take 12 years. If the growth rate increased to 15% per year, what would the new equation be and how long would it take to reach 15,000? If that was the case, the new equation would look like this. See, the original equation, that 1.1 is 1 plus 10%. Oops. 1 plus 10%. Okay, so in this case, we're doing 1 plus 15%, and as a decimal, that's going to be 1.15 to the power of t. So this is the new equation, and then I'm going to follow the same approach. I'm going to say 5,000 equals, and I'll say answer times 1.15. I'm going to count how many times I need to press equals. 1, 2, 3, 4, 5, 6, 7, 8, 8. So in this case, with a 15% growth rate, it would take 8 years. Cool. Last one here. Given this monster of an expression, we're going to start by simplifying the numerator and denominator separately. So let's see, the numerator will be 8 to the 2/3 x. Now 6 times 2/3 is 4 over x to the negative 6. Now, that 8 to the 2/3, the cube root of 8 is 2, and then we square it to get 4. So our numerator, fully simplified, is 4x to the 4. And our denominator is already fully simplified, but we don't like it because it's got a negative power of x. So this was for part A. For part B, all we're going to do is we're going to say that's 4x to the 4 times x to the 6, or in other words, we have 4x to the 10. Finally, we say if x equals 2, evaluate the final result. Well, that would be 4 times 2 to the 10. And I already told you 2 to the 10 is 1,024. So that's 4 times 1,024, or in other words, is going to be 4,096. Cool. All right. So that was the last of our examples. Let me sum up what we've looked at today. Firstly, you need to have all of these written down. If you haven't written them already, this is your chance. We have the zero index rule, the product law, the negative index law, the quotient law, the power of a power law, and the fractional index law. And recall, you may want to also note that this would be like taking the nth root of a and then raising that to the power of m. These are equivalent because the root and the power are commutative. When we have a to the m over n, that could be a to the m to the power of 1 over n, or it could be a to the 1 over n to the power of m, right? Doesn't matter because by the power of a power law, both of those expressions give us the same thing. We've discussed what surds are. We've looked at simplifying them, adding them, multiplying them. We've looked at how to rationalize denominators. Come on, Microsoft, don't act like that's not a real word. We've done a lot of examples to give you the chance to practice and check your working. Now, please complete the worksheet as a practice test. If you would like more practice questions, I recommend starting by reattempting any that you've gotten wrong from this lecture or from the practice test. It's also worth trying to make up your own questions. Now, here's my standard disclaimer. ChatGPT is a great way to make up extra questions if you prompt it very carefully to get what you want, but sometimes the questions won't work. Sometimes they will make no sense. And more than that, if you ask it to give you answers to your questions, sometimes they won't be the correct answers. You have to be really careful if you use AI. Next lesson, we will be looking at something a little bit different. We're going to be looking at linear equations and inequalities, and so I look forward to seeing you next time.